This is Calculus 12, Chapter 4.1. In the first half of Chapter 4, what we'd like to do is learn how to accurately graph a function without a graphing calculator. So all these techniques we're learning are to find key points on a graph so we can graph accurately. In many real-life applications, we are interested in the maximum or minimum values, and we call these extrema. The values are also important mathematically. In engineering, they are interested in the maximum load of a structure that it's capable of supporting, or how much pressure a submarine can take before it gets crushed by water. When graphing, extrema usually signal a change in the rate of change, so this is significant. So let's learn some definitions. Absolute extreme values. So if f is the function with the domain D, then f of c is the absolute maximum value on D if and only if f of c is greater than or equal to all f of x in D. Okay, so the upside down A is for all. And if and only if means that if this is true, then this is true. Also, if this is true, then this is true. And for the second one, we have f of c is the absolute minimum value. On D if and only if f of c is less than or equal to all f of x in D. Next, we have a theorem. It's called the extreme value theorem. If f is continuous on a closed interval, that means that it includes the endpoints a and b, then f has both a maximum value and a minimum value on that interval. So let's look at this example. This is not a closed interval, so it's not required to have a minimum or a maximum, but it can. Here is, and we look at the rest of the graph, it's bigger than or equal to the rest of the values. So this is an absolute max. This is not a min, because the limit will approach a min, but there's no value here, so it's not actually a min. Okay, we look at this one. This is a closed interval, so we'll have a minimum and a maximum. This is our local max. And we look at this, this is a min, except there's lower values here. So this is a local min. This is also a local min. Here we don't have a closed interval. This is a local min. This is a local max. This is not a max. Same reason this is not a min. This is open. So it will approach a value, but it won't ever be that value, so it's not a max. Here we have a local max. And here is also a local max. Here is a local min. And local max. And local min. And if you're paying attention, you would notice that this function does not have an absolute minimum. This goes to infinity, and infinity is neither a minimum or a maximum. Okay, we've had the definition of global or absolute extreme values. Here's the one for local. So let C be an interior point of the domain of F. This means it's not an endpoint of an interval. Then f of C is a local maximum. At C, if and only if f of C is greater than all f of x in some open interval containing C. And for part B, it's a local minimum. Again, at C, if and only if f of C is less than or equal to all f of x in some open interval containing C. Note that absolute extremum are also local extremum. This is difficult to understand until we actually look at an example, and we'll be looking at one shortly. But we need some more theorems. Theorem 2, local extreme values. If a function f has a local maximum value or a local minimum value at an interior point of C of its domain, and the derivative exists at C, then the derivative at C must equal 0. Okay, so remember, if we have a peak or a valley, our tangent line or slope is going to be 0. And definition of a critical point. A point in the interior of the domain of a function f at which the derivative equals 0 or the derivative does not exist is a critical point of f. And extreme values only occur at critical points and endpoints. Now, that doesn't mean that every critical point or endpoint is necessarily an extreme value. Okay, here we have an endpoint. It's a local min. Here we have f prime equals 0. This is a local max. Okay, because this value is bigger. Here, f prime does not exist, and it's a local min. Here we have f prime equals 0, and this is a local max. And some more, f prime equals 0. This is absolute min. Okay, it's lower than all the other minimums. Here we have f prime equals 0, but not min or max. Okay? It's a horizontal tangent, but this is not a max and it's not a min. F prime equals 0. This is an absolute max. Here, f prime does not exist. This is a vertical tangent, so it's not a min or a max either. And here's an endpoint, and this is a local min. Okay, and just again, does not mean all critical points are extrema. Let's take a look at the definition of local extreme values a little bit more closely. And you'll want to check with your prof to clarify whether min or max is strict or not. This is strict and this is not strict. Strict is better to work with because it eliminates the horizontal line case. So if we have a point f of C, this is C, and f of C. Remember, f of C is the vertical value. C is our x value. we take some neighborhood. This is bigger than or equal to. It's also less than or equal to this neighborhood. But it's not a minimum or a maximum value, because if we take the neighborhood out further, we can see that there's a minimum value over on the right-hand side. And again, if we take the neighborhood further out, then there's a maximum on the left-hand side. So tricky to say. Min or max. Okay, but if it was strict, we know that it's not bigger than all the values around it. It's not smaller than all the values around it. So it's not a min or a max. But generally, we don't deal with horizontal line segments very often in this course. This is just a tricky case, and this line could go on for a very long time and then go up or down. So that's what makes it tricky, especially if you're using a graphing calculator and you only see this horizontal part and you don't miss this part and this part. Okay, finding extrema part 1, and we're going to do this algebraically. We need to compute the derivative and find the critical points. And the critical points are where the derivative is 0 or does not exist. Then check graphically if the critical point is an extremum. Check the endpoints if they exist are extrema. This we won't be doing graphically later, but for this chapter, just do it graphically. Okay, so let's look at some examples. Note, you should recall that the derivative does not exist, and this can occur on boundaries of piecewise functions. Okay, so we're looking for the derivative, g prime of x equals e to the negative x times negative 1. So we have negative e to the negative x equals 0. And no solution. Okay, recall that e to the negative x looks like this, and it has an asymptote. And the asymptote is y equals 0. So we will never find a solution for this. So we need to check the endpoints. Check endpoints. G of negative 1 equals e to the negative 1 equals e to the 1, which is e. G of 1 equals e to the negative 1. So this is 1 over e. That means this must be our absolute max. This is our absolute min. Just remember, we're always doing derivatives and we're just finding zeros. Okay, derivative, e to the negative x squared, d dx, negative x squared, e to the negative x squared times negative 2x. So we need to solve negative 2x e to the negative x squared equals 0. Negative 2x equals 0 because we don't divide both sides by this. It's okay to divide by this because this never equals 0. So x equals 0. We evaluate k of 0. This is e to the 0, so this is 1. Now we need to do the endpoints. And since they don't exist, we need to do limits. Limit as x goes to negative infinity, k to the x equals and we use direct substitution. E to the negative infinity squared. And this equals 0. Okay, so this becomes positive infinity, and then this is negative infinity, and we know that that's going to be 0. Let's do the limit as x goes to infinity. K to the x equals e to the negative infinity squared. Again, this is infinity, negative infinity. This one's also 0. So that means this is our absolute max, and we have no min. Okay, again, this is an asymptote. It won't ever go to 0. And the other clue is this is not a closed interval, so we're not required to have a minimum value. This is an open interval. And that completes this lesson.